So today we're going to talk about the state pattern. The state pattern is going to be an application of polymorphism. Polymorphism is enabled by inheritance. To learn inheritance, we had to talk about classes. To understand classes, we need to know what objects were. So we've been going down this progression of OOP, and we're reaching the pinnacle of the state pattern, which relies on all of that information, all of that knowledge. With that said, I'll be perfectly honest, I don't really care if you understand the state pattern by the end of this semester. Like if you walk out of 116, obviously I need you to know it for project 2, but if you walk out of 116 going, man, I don't really understand that state pattern stuff, I'd be okay with that. What I'm using the state pattern for is to reinforce your understanding of polymorphism and inheritance, and those are the things that I need you to know. Walking out of 116, I need you to be like, I know the hell out of polymorphism and inheritance. The state pattern is an application of polymorphism. It's something that can't be done without polymorphism. And, well, it's a little bit too strong of a statement, but without getting into technical details, we need polymorphism to use the state pattern, and I'm using it as a way to show you something cool that you can do with polymorphism. But I'm using it as a tool to reinforce your understanding of polymorphism, and that's really shown in the syllabus. In this learning objective, state pattern doesn't show up anywhere. Inheritance and polymorphism sure do, but nowhere in the learning objective, like during your interview. I don't know if I'm willing to go that far, but in your interview, I'll go this far. In your interview, you won't get a question like, what is the state pattern? Your questions might use the state pattern as an example of polymorphism still. So if the TA asks, can you give me an example of where you've used polymorphism and you explain the state pattern, perfect. But the TA should not, if they do, let me know, should not ask you just straight up, what's the state pattern? Because it's not a learning objective. It's not on this list. That means we don't ask about it. On your quiz, I don't care if you understand the state pattern, but I do care if you understand inheritance and polymorphism. So there could be a state pattern question, because if you understand polymorphism, it doesn't even matter that it's the state pattern, you just understand how polymorphism works, and then you can go through the state pattern. But we're not going to ask you about state pattern directly. Right, you do need the state pattern, but again, it's an application of polymorphism. Can you use polymorphism in a creative way? And for our purposes, that's the state pattern. The state pattern is not strictly speaking, isn't a learning objective of the course. Just want to make that clear because I get a bunch of questions about that. Well, we're way past unit testing. Let me just go up. Just in case any of you forgot, I'm not even using my own feature here. You can collapse these and get down to where we need to be quickly. So with that, let's learn what the state pattern even is. The state pattern. So the state pattern is a design pattern. So what's a design pattern? So there are quite a few design patterns in object-oriented programming, which are approaches to solving common problems. There's certain sets of problems that we just always face in our code, and there's this gang of 4. This was 4, I believe they were software consultants. They got together and they said, hey, look, we keep having teams that have these same questions, these same problems. We always get the same answers. Why don't we publish those answers and just release them to the world and let everybody know what they are? So they came up with a whole bunch of what they dubbed design patterns, which are solutions to common problems. We've used one of them, adding modifiers to items. That's a design pattern. I blanked last lecture on what the name is. I'm not going to think of it right now. But it is a design pattern. I don't even see it as a design pattern because I see it as so fundamental to object-oriented programming. But it does have a fancy name, and it's in the Gang of 4 list of design patterns. These are really nice approaches to solving problems that if you're out there writing code using OOP and you come across a situation where you're not really sure how to handle the question, handle the problem, check out design patterns and see if there's a design pattern that's just sitting there waiting for your problem, waiting to solve your problem, because there might be. We're only going to talk about one of them, explicitly at least. the state pattern. State pattern, as I just went over, is an application of polymorphism, and that's the most important part for the context of this class of the state pattern, is it's helping you understand and use polymorphism. We've seen polymorphism, we saw it in action a little bit, but nothing like too wild that we did with it. The state pattern is going to give us something to really do with polymorphism that, at least in my opinion, is pretty exciting. I like the state pattern. I'm biased towards it. But for this course, as an educational tool, we're using it to understand further polymorphism. So we already know that each object contains state and behavior, and the state of an object can influence its behavior. So if a state variable has a different value, it's going to change what's returned from the behavior, from the methods of that method. So if I have an array and it has 4 items in it and I call .size, I'm going to get the value 4. If that array has 6 items in it, I'm going to get the value 6 from size. So size, the method, had different behavior depending on the value stored in a state variable. And that's common. We've seen that since like the first time you've written code and like asked a string for its length, you've seen that. But what if we want to really change that behavior? What if we want a method that does extremely different things? So what if I call .size on an array, and instead of getting the number of elements in the array, I want to get the sum of the total size of all of the elements inside the array. So maybe if this is an array of integers, I want it to sum up all the integers. If it's an array of strings, I want it to sum up the total number of characters across all strings. What if I want that behavior? Very, very different behavior from the size method. How would I do that? We don't we don't really have a mechanism for it, but we do. We have conditionals. So we would use conditionals typically for that. Of course, they're banned on your homework, unfortunately. So we would usually use conditional. If some Boolean expression, do this, else do that. This is how, this is just how we do that. We get different behavior by throwing a conditional at it. And I want to make sure this is clear. So first of all, test 1 and 2, you probably didn't really miss conditionals. There was only one spot where you would really kind of want a conditional, and when you're scanning an invalid barcode and you want to return a new item with error 00, that's about the only time where you really missed your conditionals, I would assume. It's designed to make it so you don't really want conditionals. In that one spot, I gave you the clue right in the homework. I said use get or else, and it'll replace that conditional. It'll do what you would be doing with that conditional, but in a method call where you don't have to violate the condition of the assignment. Task 3, which we're starting task 3 content right now. Task 3, you're going to miss your conditionals. You're going to miss them a lot. It's designed that you're going to want to make decisions in your code where different pieces of code you write are ran conditionally based on some Boolean expression. That's what you'll want to do. That's what your instincts will tell you to do, but we're not going to be able to do that. So what I want to make clear is that I am in no way saying that conditionals are a bad thing. I do get that misconception with this homework, that I don't want to make it sound like, oh, moving forward, the state pattern is what you use, not conditionals. That's absolutely false. I'm banning conditionals to force you to use the state pattern at least once in your career so you can at least get a taste of what it's like to solve problems the OOP way. And then moving forward in your career and your future programming that you'll do, you have that tool in your toolbox, and when you approach a new problem where you got to change behavior, you can say, well, should I just use conditionals or should I apply the state pattern? Which one makes more sense for this specific application? And a lot of times conditionals will be the answer. I love conditionals. I use conditionals all the time. But there are specific cases where I pull out the state pattern because that's a better solution for that specific problem that I have. Usually when this is the case is when I'll pull out the state pattern. Well, I have a whole lot of really different behavior that I can't easily change through values stored in state variables by just saying, well, this value is this, I'll get different behavior. Like a mathematical equation. No matter what the value is, any different value, you get different behavior, but not like significantly different behavior. So if I have significantly different behavior that I can't just change through values in state variables, this is where I would start using the state pattern. So what if you have this code? If this Boolean expression, something, else if, this Boolean expression, do something, else if, else if, else if, else if, else. I got tons of different behavior in the same object. This is fine. Again, in no way am I saying you shouldn't do this. I have this exact pattern in a lot of my code. I usually don't like it. I usually try to avoid this, but sometimes it's just the easiest thing to do and the best thing to do. But there are downsides to this. It's hard to read, first of all. If somebody else wrote this method and you're joining the project and you have to read this and understand what it does, it takes a bit of effort to see what's going on here. You have to look at what those conditionals are, see which one's going to be hit, and in what order they're going to be hit. It's hard to maintain if you want to add a sixth behavior here. Where do you put it? So the way else if works, well, as we all know, like if this conditional is true, these next two conditionals never get checked. So we have to think about the order in which we put them. If we have a new behavior that we want to override the next three, we put it up here. If we only want it to override the third one, we put it here. That order really matters. And then when we add that, when we have that change and add that new behavior, guess what we're doing? Going back to our unit tests and rewriting those, adding more tests, and potentially changing the existing ones to make sure that we get the expected behavior that we want. It's going to end up being a lot of work as you get more else ifs here. It gets to be a lot of effort to modify your code. Your code gets very rigid, and it's hard to add new features. Your customers come to you and say, I would like this software to do this thing, this new feature I'd really like. And you're looking at your code like this, which is probably in a file that's hundreds of lines long, if not thousands, and it's going to be very difficult to add that feature. Let's try the state pattern. Let's see an alternative and give you a different approach to that problem where you have one object that needs a lot of different behavior under different circumstances. So let's try the state pattern. For the state pattern, instead of relying on the values stored in our state variables, we're going to have a state variable that has an object that's a reference to an object that's going to control the state. That variable is going to have an abstract type, and it can store different concrete types that extend that abstract type. So we don't really know what type that object is at any given time, but we're going to defer to that object for our behavior, and depending on what type it actually is at any given time, when we ask it for our behavior, it's going to give us different behavior depending on its type. So if it's a different type, it's going to give us different behavior, and then we'll have different types for each set of behavior that we want. So what we'll end up with is very modular code. We're going to have a whole bunch of different states that implement small pieces of behavior that are going to give us a lot more classes, a lot more methods, but each method that we implement should be a lot smaller. And we're going to see the shift. You'll see the shift in task 3, where the bulk of the work of task 3 is at the design level. You're going to have to design how you want to lay out your code. You're going to create multiple classes that are not defined in the homework doc, never even mentioned in the homework doc. The homework doc doesn't even mention the state pattern. It's up to you to realize what classes you want to create, how you want to organize them, what each one should do, and then defer to the behavior. There's a lot of design work there setting all that up, and then when it comes time to writing your code, writing the code should be trivial. As long as your design is solid, writing the code for task 3 should be really easy. Setting up the architecture is going to be quite difficult, though, especially because it's one of the first times, really Project 2 in general is the first time you're really designing code. By design, no pun intended there, but the homework is designed to get you to start thinking about how to organize and structure and design your own code. And task 3 is where it's going to hit you hard, give you a lot of practice with that. So we're going to create an abstract class for the state, which is going to define our API. Now, API is one of those terms that's, I think, pretty overused in computer science and programming. Our API in this case is going to be the set of methods defined in our abstract class. So those are the methods that can be called, the methods that we're going to defer to the state for behavior. And that's what I mean by API when I say it in this context. It's used in a lot of different contexts. I use it in a lot of different contexts as well. It's a very versatile term. But I'm going to use it in the state pattern to be the set of methods defined in the state abstract class. Those methods need to be implemented each time we extend that class, each time we inherit that class, and that each state that we can be in is going to define all that behavior of the API. But the API itself is just the list of methods that can be called. Oh, and each state, spoilers, each state is going to store a reference to the object to which it's attached. Yeah. Application Programming Interface. I was realizing that as I was doing this slide, like I never even expand the acronym. Yeah, Application Programming Interface is API. It's how, in general, it's how you interact with software, is the general meaning of the term. Is it okay to use the state pattern for task 2? Yeah, I ain't going to stop you. But the state pattern, like task 3 begs for the state pattern. Task 2, if you find it helpful, that's fine, but it's not designed to need the state pattern. I would expect most of you would not use the state pattern for task 2, but if you do, that's fine. Okay, so what the hell does all that mean? This is one of the cases, depending on each topic, I like to structure my lecture a little different. For the state pattern, I think it's helpful to get all the technical definition stuff out of the way, which I just did on the last few slides, and then go into the example. For other topics, I like starting with the example and then doing the technical stuff. I think this one works better if I start with the technical stuff. So I got all the words out there, but what the hell does any of that mean? Let's talk about it. Let's talk about it through an example. So meet Bruce Banner. For those of you who don't know, he's a world-class scientist. He keeps his cool. He can drive a car. We'll see why that's relevant. And he's not very helpful in a fight. For those of you who actually don't know Bruce Banner, it is a fictional character. This isn't a real person that I'm picking on throughout this lecture. Just in case somebody hasn't heard of Bruce Banner, which is possible, I guess. And no worries if that is the case. But Bruce Banner, or as I'll call him, Dr. Banner, cool-headed, scientist, great. But if you make him angry, he becomes the Incredible Hulk. When Bruce Banner is the Hulk, he has very different behavior, extremely different behavior than when he's Dr. Banner. In this case, he's not going to drive a car, he's just going to smash the crap out of it. And he's really good in a fight, but he doesn't have any control. He just goes crazy. He's just wild. Very different behavior. He's just one person, but depending on what state he's in, whether he's Dr. Banner or the Hulk, he's going to have extremely different behavior. So let's simulate this with code. Let's start using some code and try to write software that's going to simulate this transition, this one being that can have two very, very different states and different behaviors. Behaviors that we're not really going to be able to just have some state variables that are going to define how the behavior should change. I mean, we can, and I'll talk about that later, but very, very different behavior. Not just slightly different. Like the length of a string. That's going to have slightly different behavior depending on the current situation. This is very different behavior. So let's set up our state pattern. So instead of relying on the values stored in state variables to be able to change our behavior, we're going to rely on the type of a state variable to change our behavior. Switching from values to types is our big change, which we're going to do through polymorphism. So instead of actually implementing methods, we're going to have these 4 methods. This will be our API, the list of methods. Make angry, calm down, use car, which takes a reference to a car, which I don't show the code for car in the slides, but it's in the repo. Just because I didn't want to clutter up the slides too much, I didn't add it here. It doesn't really do anything, it just prints a few things to the screen. It's a boring class. But I will call some methods on it. It doesn't matter what those methods do necessarily, but I just want to show the state pattern of what it could do. And fight. So all of these methods don't do anything. Methods don't do anything. There's no code. There's no actual code here. I didn't define any behavior for Bruce Banner. This is going to be common in the state pattern, and I'll draw the parallels throughout the lecture, but Bruce Banner here is going to be your self-checkout for task 3. So your self-checkout, most of the methods, the API that's there provided for you, you shouldn't have much code in there. You'll have code in there through task 1 and 2, but when you transition to task 3, there shouldn't be much actual code that does stuff in that class. Instead, we're going to defer to the state. And by the way, I'm going to say the word state like 100 times in this lecture, at least 100 times. We're going to defer to the state for the actual behavior that we should get. So I don't know, when I call make angry on Bruce Banner, I don't know what it's actually going to do. I'm just going to tell the state, hey, state, make angry was called. What do we do when someone makes us angry? You're going to ask the state. The state is going to have a specific concrete class, that extends it or inherits it, which is going to contain the actual behavior of each method. So in Bruce Banner, we just defer to the state and say, hey state, this method was called, what do we do? The state abstract class is going to define the API, which is just the list of methods for which we're going to defer to the state for functionality instead of implementing that functionality in the base class itself. So we're going to defer to the state for these 4 methods. And then for each state that we can be in, we extend that abstract class and implement those 4 methods. So for the Dr. Banner class, we're going to extend state and implement these 4 methods. And then we're going to have an initial state, which is going to be an object of one of the concrete types, one of the concrete state types. So I'm going to say when we first create a Bruce Banner object, which the parallel breaks down a little bit there, that we can have multiple Bruce Banners, but when we create a Bruce Banner object, when Bruce Banner is born, he's going to be in the Dr. Banner state, because that's going to be what we'll set our state variable to initially. It'll be in the Dr. Banner state. Bless you. So whenever we're writing the class that's going to have the state attached to it, that we're going to apply the state pattern to, we don't really care about the functionality. We're just going to defer to the state. We have a variable of type state. We know that it has these 4 methods that on purpose match the 4 methods of the Bruce Banner class. And we just defer to the state for functionality. The state's going to decide what actually happens in each one of these methods. And the state is going to have a reference to the object to which it's attached, which we use this for that. New Dr. Banner of this, which will be a reference to the object that's being created. This will be called in the constructor. In the constructor, this is a reference to the object being created. So the state is going to have a reference to the object to which it's attached, which will be important. I'll explain in a few slides, but it'll be important so it has access to the state variables of that object. So we extend this class for each concrete behavior. Oh, did get a little ahead of my slides. So when we're implementing these concrete classes, when I'm implementing Dr. Banner, at this point, this is where things should get fairly easy. So the hard part is looking at, designing this code, looking at the Bruce Banner class, and deciding that I want 3 more classes, an abstract state class, and then 2 concrete classes for the states that I can be in. What methods are going to be deferred? In this case, all of them are going to defer to the state for functionality. Once I have all that set up, and I'm going to use inheritance, of course. Once I have all that set up, things get a little easier. Because now the questions get very narrow in scope, very narrow in focus. When I'm implementing these methods, I'm thinking of one piece of functionality. when Bruce Banner is in the Dr. Banner state and somebody calms him down, what should he do? What should the behavior be? And of course, for the lecture example, I'm just printing things to the screen, but this is where you'd have a few lines of code to define what happens in that exact state. Instead of that code being buried in a giant else if statement, that code is going to be separated into a very readable piece of code. We're in the Dr. Banner state, and somebody calls calm down, what should happen? We're in the Dr. Banner state, somebody calls use car, well, he should just drive that car. The Boolean here is whether you're going to damage the suspension or not. He's not going to damage the suspension, he just drives the car as normal. When he's in the Dr. Banner state and he's in a fight, well, things aren't going to go so well. When he's in the Hulk state and somebody makes him angry, what's going to happen? When he's in the Hulk state, I won't go through, and he uses a car, I won't go through all of them. I guess I'm only skipping one. He's going to smash the car. Very different behavior here. We're going to either call the smash method on the car or we're going to call the drive method on the car. Very different behavior. Same object. We said this Bruce Banner object dot use car, but depending on what state Bruce Banner is in, he's going to have very different behavior. And I purposely skipped these two. I'll talk about those in the next slide because I skipped ahead a little much. So each one of these classes, each one of these states will have a reference to the object to which is attached. So each one of these states, Dr. Banner and the Hulk, have a reference to their Bruce Banner object which stores them. So this means that they have access to all the state variables of that Bruce Banner object, including the state itself. Now, we only have the state itself in this object, but for your self-checkout class, going through tests 1 and 2, you have a good number of state variables in your self-checkout, and in each one of your states, you're going to want to be able to access those state variables. So if each state has a reference to your self-checkout, they'll be able to access that. Self-checkout reference dot display string, whatever you want to access, including the state itself. Here, the state itself is the new thing. So each state can replace that state variable with a new object. This is what we call a state transition. So when a state is modifying, or anything, when something's modifying the state of that object, it's going to be a state transition. So for example, when Bruce is in the Dr. Banner state and somebody makes him angry, he's going to transition into the Hulk. He's going to transform into the Hulk, and he's the Hulk from then on until he transitions back. So we're going to take that reference to the Bruce Banner object, access its state variable, and set it equal to a new object of type the Hulk, and then forward that reference to Bruce Banner to the Hulk, because every state is going to need that reference to be able to, at the very least, perform state transitions. So when he's in the Dr. Banner state and we make him angry, he's going to become the Hulk by replacing the type of that state variable. Which is named state, which is of type state. Kind of overused state quite a bit in this lecture. But we're going to override that. So if we have Dr. Banner, we call make angry, and then we call another method after that, all 4 methods will have this behavior now, because this variable has an object, a reference to an object of type the Hulk, we get all this behavior instead of this behavior. If he's the Hulk and someone calms him down, we have a state transition back to Dr. Banner. So if he's the Hulk, we call calm down. Now we have all this behavior because that variable named state is going to store an object of type Dr. Banner. And when we defer to that state for its functionality, it's going to give us all the Dr. Banner behavior from these Dr. Banner methods. Putting it all together, here's our 4 classes. So Bruce Banner has a reference to an object of type state. State is an abstract type. So depending on what actual type is stored in that variable, that's going to change the behavior of that variable, and then we defer to that variable for all of the functionality. We don't define any functionality in Bruce Banner. We just say, hey, state, this method was called. What do we do? Initially, we're in the Bruce Banner state, so we'll get this set of functionality. As soon as we hit a state transition, this variable will have a different type, a reference to an object of a different type, in this case the Hulk, and then we'll have all this behavior. So we get very different behavior and changing behavior, of course, with no conditionals. Yeah. Yeah, so we have a few options there. If you want the same behavior across both states, you could either put it in Bruce Banner. So we can have concrete, and I'll have an example of a concrete method in this, a method that doesn't defer to the state in a minute here. But we can put a method here that doesn't defer to the state, and that's us saying, I don't care what the state is, this method always does the same thing. So like in self-checkout, if you have a button that always does the same thing, you can just keep it in self-checkout and not defer to the state. Another option is to put it in the state class itself as a non-abstract method. So if we put it in the state class as a non-abstract method, that'll be the default behavior for every state. And then if we want to change that default behavior, we would override it, which gives us a lot of flexibility. If we have like 10 states, 9 of them should do the same thing, but the 10th one shouldn't. We define that in the state class, and then just override it in the 10th one, and the other 9 just inherit the method and just use it as it was inherited from the state. So a few options for that one. But we have a lot of flexibility when it comes to this. Do we need to make a new object each time we have a state transition? No, but it's simpler that way. So for first learning the state transition, the state pattern and everything, I'm fine with it. That's the way my lecture examples are going to go with new objects. If you're worried about efficiency, it would be a little more efficient, and if you want to set up your self-checkout, your homework project 2 this way, that's perfectly fine. If you want to set it up in a way that you don't create new objects, but instead you store a list of references for all the states, like when you create Bruce Banner, for example, in the constructor, you could create instances of each of these classes, store references to those 2 objects, and then for your state transitions, just switch to the reference that was already created, instead of constantly creating new. Like if you just keep switching states here, you're creating a lot of new objects. It's a lot of clutter. It will be garbage collected, but it's still, you gotta allocate heap space. Like it's inefficient. For understanding the state pattern, I'm fine with it. But if you're worried about the efficiency, you definitely do not have to create new objects of these types each time. In 116, we generally don't worry about efficiency much. We're still learning new programming concepts. And then in 220, 250, I'll let them straighten you out on efficiency, optimizations, and things like that, and the rest of your career, really. The way I look at the curriculum and your, well, maybe not careers, but the curriculum is your first 2 semesters, at least CS 115 and 116, you're learning how to write code. You're learning how to get stuff done. Now we're focusing on like architecture of your code and trying to get big projects done and working. And then the other 3 years is all about optimizations, how to do things better. So I'll save that for the next 3 years. I don't want to steal all their thunder. And some courses are like specific applications, specific domain spaces, for example. Like I teach web applications. I'm not necessarily working on efficiency there, but we're entering a new domain space. But a lot of the next 3 years is how to do things optimally and better. But I'll save it for them. Right now I'm doing whatever I can to keep the code as clean as possible and as simple as I can, because this is a complex topic. So I don't want extra things bogging down your mind. Because it would be extra code, it would be extra fluff in here to set that up. But you absolutely can. Okay, but we also have a pretty big problem here. If I gave that to you as a problem, if I said, create this Bruce Banner that has two different sets of behavior, you're going to have a state variable that's a Boolean that says, is the Hulk. It's going to start out as false, and then every one of those four methods, you're just going to have a conditional. You're going to say, make angry. If is the Hulk, do this, else that. If the Hulk, do this, else that. And your state transitions would be changed to, is the Hulk equals true, is the Hulk equals false. You could definitely argue that that's a lot simpler than this. It would only be one class instead of four, a lot less complexity, probably even easier to read. You'd probably be right. You'd probably win that argument if you said, why don't we just use a conditional here and a Boolean flag? So kind of an issue here. Why learn the state pattern? The power of the state pattern, where the state pattern really comes in, is where we have more states. Just like the game object class, I said, okay, we have health potion and dodgeball because that's, I can't fit too much on the slides. So I showed you inheritance and polymorphism with two different types. But what if we had hundreds? I left it to your imagination. Like imagine that we had hundreds of different types of objects. You could start really seeing the payoff here. Same thing with the state pattern. With two states, we don't see too much payoff. But once we have more states, we start seeing more payoff. Let's meet Professor Hulk. This is a third state that Bruce Banner can be in. This is where he's transformed as the Hulk, but he has full control. He gets the best of both worlds. He still has his scientist brain, but he also has control. He also can win in a fight quite well. He's got everything. With the state pattern, we're going to create a new state. We do that by inheriting our state class. And then we implement these four methods for Professor Hulk. And we're doing the same thing we did before. What should Professor Hulk do when you make him angry? What should Professor Hulk do when you calm him down? What should Professor Hulk do when he uses a car? He's going to still drive it, but he's going to damage the suspension. And what should he do when he fights? Well, he's still going to smash, but he's going to do it in a controlled manner. He's not going to be out of control. Four different behaviors for these methods, different from the other two classes. But when we're implementing this code, we don't have to think about it too hard. We're just implementing what he should do in this new state. And notice that we didn't modify hardly any of the other code. We didn't even touch the other two states. We didn't touch the state abstract class. All of that functionality just remains. And then we're going to add our state transitions. Now, I cheesed this a little bit because I put my state transition in the Bruce Banner. But even if we had state transitions from Dr. Banner or the Hulk, that's the only code we would change in those classes. We would just add our state transitions in. When should we transition to Professor Hulk? I'm going to put this method right in Bruce Banner, because I'm going to say whether he's the Hulk or Dr. Banner, he's going to transition into Professor Hulk. I don't care which state he was in when he figured out how to learn control. He's going to transition. So this is a method that's going to do the same thing no matter what state we're in. So in your self-checkout, you have some functionality that's the same across every single state you have. You can just put it right in the self-checkout class itself. So when he learns control, he's going to transition to Professor Hulk. And for what it's worth, he can't transition back in my example. According to the lore, he can now, but in this example, in this code, he's not switching back from Professor Hulk. And we didn't modify any existing functionality. This is important because that Dr. Banner and Hulk classes that we wrote, that we have testing for, that we know it works, we made sure everything worked with those. We don't want to modify those because then we got to retest them. We got to make sure it still works with the new functionality, which means writing new tests. And you know how much of a pain it is. By now, you all know how much of a pain it can be to write tests. Sometimes writing the tests takes a lot longer than writing your code itself. So if you got these classes and you got these tests, this nice big test suite, testing every single possible bit of functionality in them, and then you go and change the code all around. Maybe your tests don't even run anymore. Maybe you change the behavior that much that you got to rewrite that test. Well, that's a lot of extra work. And I don't want to do extra work. I want to be as efficient as possible. So that's going to be tougher. So for example, if you have your Boolean flag, is the Hulk, if true, do this, else do that. Well, now we want to add this state. Guess what you're doing? You're refactoring all of your code. You have a complete rewrite on your hands to be able to add that third state if you're not using the state pattern in this example. You got to change your Boolean flag. You can't even use a Boolean anymore. You might change that to an int, where that int can be 0, 1, or 2 to represent the 3 states, which is going to be harder to read because you're having magic numbers that just represent things. And then, or maybe you use an array of strings to make it a little more clear, or an enum. But you're going to have something to represent those 3 states, and then say if, else. You're going to change every single method, and then retest every single method. Pretty much trash your whole test suite and rewrite all of that as well. You're basically starting the project over at that point to add this new feature, to add this new state. In the state pattern, it's not even a big deal. We just add the new class, test the new class, and add our state transitions, and that's it. We're going to reuse all those tests. We're going to reuse all that old code. And since we didn't even touch the old code, it's got to still work, right? So we added functionality. I got to talk about this slide answering the question earlier, so I'll really skim it this time. But if we want functionality that's the same across all states, we can put it right in the base class, self-checkout for your homework. Or if we want default behavior in a state, we would implement functionality in the state class and then only override it if we need to change that default behavior. Any questions at this point? We're almost at the end here. Why do we put this here if it's never used? The way I set this up, I need that to be able to forward it to the state abstract class because the state takes a Bruce banner. So I need that just to satisfy the abstract class constructor. But yeah, we don't use it. Oh yeah, we don't use it at all, do we? So you could, I guess, it doesn't hurt to have it, I guess. But yeah, we could get rid of that and then just pass null here, I guess. I guess that would be valid, since we never do use that. But generally, like for your homework, you're always going to use that reference. I don't use it here because I don't have any state transitions, and I don't have any extra state variables. So like for your self-checkout, actually, I'm gonna piggyback on that and go into something else. For your self-checkout, you already have a bunch of state variables in your self-checkout. I feel like I just said this. Did I say it in the last lecture or earlier in this one, though? It was in this one? Okay. So you're going to have a bunch of state variables in your self-checkout, and you'll have a reference to your self-checkout in all your classes, and you use that to access all your state variables, including the state itself, to be able to have state transitions. So you'll always want a reference. Just this example is a toy enough example that I happen to not actually use it. But you'll want that reference in all of your states. Can we use traits? Yes. Yeah, so in the homework doc, since I don't even mention that you need the state pattern, I don't mention how your states have to be set up, you can use whatever you want. If you want to use states instead of traits instead of abstract classes, knock yourself out. If you don't know what traits are, don't worry about it, just use abstract classes. So to visualize this, as we're talking more about design things, it's nice to be able to visualize what's going on. And in office hours, the TAs and I like to ask you for your state diagrams like this. So it's very helpful to write out a state diagram when you're designing the state pattern, which is going to capture all of the states that you can be in and the state transitions between them, and also the initial state that we're in. So we're going to start off in the Dr. Banner state. If you call make angry, we transition to the Hulk. Calm down, transition back to Banner. Learn control from either Dr. Banner or the Hulk, and we enter the Professor Hulk state. And there's no leaving the Professor Hulk state, no arrows going out of that one. You want to do the same thing with your self-checkout. Visualize what states you can be in, what transitions there are between them and what behavior should be in each one of those states. The T's and I like to, if you don't have one, we like to ask you to draw one. Like, draw out your states, visualize it. Usually when you draw out the state diagram, you'll find your own bugs, your own design flaws. So for the homework, or any time you're using the state pattern, design your API. For the homework, this is already there for you. The self-checkout class already has all the methods implemented. And like I said, it won't hurt to just defer all of those methods to the state. If you want to do it that way, if any of them have the same behavior across all states, you can just leave it in the self-checkout class. Once you have your API, decide what states you need. The general approach for this is any time you have a situation where any button should do something different, or any of the API methods should do something different, you got yourself a state change. So if I have an item with barcode 1, 2, 3, and I hit 1, 2, 3, enter, like after hitting 1, all the buttons do the same thing. 2, all the buttons do the same thing. 3, all the buttons do the same thing. I hit enter, and right when I hit enter, the enter button will have different behavior. It's going to have that rescan behavior after I hit enter. I'm thinking state change. I just had a state transition the second I hit that enter button. So we entered a new state. The buttons have a different set of behavior. If I do something else, like if I hit 1, I have another state change. The enter button goes back to doing what it used to do. I have another state transition. Anytime any button changes its behavior, you have yourself a state transition. So think about that when you're designing your states. And then add in your transitions between the states. Make sure you get those transitions in there so you're switching states properly. Any questions? Does learn control need to be an empty body in the abstract class? No. So learn control, I don't defer to the state at all. I never call this.state.learn control, so it doesn't need to exist in the state. I'm never deferring to the state for this like I am the other 4. The other 4 I'm deferring to the state, so it needs to be defined in state. But learn control, I never defer to the state for that functionality. I could, like if I changed the code, I could defer to the state and then implement it there. I just chose not to for this example. Have a great day. I'll see you all Friday.